when you're ready.
Sound. All right. Tell me if this doesn't work, but otherwise I'll press play.
Mic off.
Yeah, we can hear it. That's great.
Integration is a mathematical principle founded on the work of Stanislaw Ulam. It employs a non-deterministic approach to the process of integration, meaning the final outcome is an estimation of the correct value with corresponding error bars. Amongst those error bars is likely the correct values. This process has given rise to a broad category of computational algorithms known as the Monte Carlo methods. Developed by Ulam during the height of the Manhattan Project, the methods needed a code name to help classify the algorithm. Ulam suggested Monte Carlo after the city his uncle gambled in. The algorithms utilized probabilistic metaheuristics, a higher-level procedure designed to generate a partial search algorithm, known as a heuristic, that provides a sufficient solution to an optimization problem, particularly with limited computational capacity. Given the cultural zeitgeist of the mid-40s, it was necessary to develop a mathematical principle which could operate with little computorial capacity, as much of the computers were analog machines being utilized so heavily they frequently broke down. By utilizing methods which were operable on limited computer systems, Ulam strained the machines he had available to him significantly less, as well as unknowingly creating a very strong but lightweight integration method for future generations. In modern times, Monte Carlo methods have been redefined to contain a range of specialized algorithms in fields like physics, physical chemistry, and operations research. They also have applications in much more specialized research scopes like quantum physics, genetic heuristic-like particle methodologies, which find its origins in work done by Alan Turing. While there are some alternatives to Monte Carlo integration, the method remains popular, even today some 60 plus years since its development. Monte Carlo integration and its real-life use case can be seen within finance as a risk assessment technique. Applied as a simulation to solve probability of different outcomes on problems that cannot be simply solved due to the interference of a random variable, this application is seen mostly within the fields of valuation of options, portfolio valuations, valuation of fixed income instruments and interest rate derivatives, and financial modeling. Within valuations of options, Monte Carlo simulation is applied in pricing equity options, where simulations are run on each of the share prices to its possible path, determining their option payoffs. The payoffs are then averaged and discounted, providing the current valuation of an option. Monte Carlo simulation is also utilized in portfolio valuations, where simulations of portfolio value influencing factors are used evaluating a portfolio. Then the simulated portfolios are averaged to determine the value of the portfolio. Monte Carlo is also applied when evaluating fixed income instruments and interest rate derivatives. The underlying uncertainty within fixed income instruments and interest rate derivatives is the short rate. Simulations are run multiple times on the short rate, determining the price of a bond or derivative for each simulation. The obtained rates are then averaged to provide a rate on determining the current valuation of a bond. Monte Carlo simulation is applied in financial modeling through Excel on executing sensitivity analysis. This tests the volatile assumptions and variables that influence net present value, or NPV, of the business. Monte Carlo integration is common in computer mathematics. Originally designed as a model which is then used to determine various unique outcomes, it allows users to predict their results throughout their inputs of values, uncertainties, along with their risk factors. It's through this integration that has been applied to various systems that allows users to understand the result of randomness in correlation to risks of their predictions. A method known as sampling can be identified as an ideal use of Monte Carlo integration. Information is collected from as many random scenarios or objectives through their repeated cycles of said scenario. The goal being to draw as many outcomes as the user requires. This ability to display every potential outcome establishes Monte Carlo integration as a valuable and sometimes essential asset. The sheer number of results that can be cycled through using the multiple choice system, the Monte Carlo system, allows users to repeat the process as many times as they need. The final result arrives where the possible outcomes are listed in the form of probability distribution. Essentially, the Monte Carlo system tells the user the possible outcome, what could happen, and how likely the chances of that outcome happening. To compute simple integrals, you must compute a series of complex operations to find the antiderivative and apply a subtraction to reach the desired interval. Integrating a function can also be graphically seen as the area under the function curve. By only knowing the function, the goal is to estimate the integral of the function over a certain interval. Here, Monte Carlo methods can help. Monte Carlo integration is a special method of numerical integration, but instead using random numbers. Say we want to integrate a function f of x from a to b. By taking a random point between x and multiplying it by b minus a, we can calculate an estimated area, which is shown on the screen. This, of course, is just a vague estimate, which can drastically over or underestimate the actual integral. However, by evaluating the function at many different random points x, adding the result integral and averaging the results, the product gets closer to the real result. This is illustrated in the example on the screen. The more random numbers taken and resulting integrals calculated, added, and averaged, we get a very accurate result. The following calculation can be shown with the formula on screen, where n is the number of different samples that are used in the calculation. Lastly, it is possible to create a Python code, which takes a set of variables and performs Monte Carlo integration on those variables to produce an approximation in integer or graph form. The Jupyter Notebook for this process is shown on the screen at the moment. In this specific example, we are integrating between 0 and 1 on the function x squared over 1,000 error bars. As previously described, Monte Carlo methods produce error bars beyond the expected result. However, the correct error bar will have the greatest frequency. It is clear in the example that the algorithm is most frequent around 34, by printing the variable answer. We are able to confirm this with Python, producing an approximation to a significant number of decimal points. In conclusion, Monte Carlo method is a way to approximate functions by using little computorial power. Having its roots in the Manhattan Project, the integration has been used for many different reasons in many different fields. Due to how lightweight it is very easy to make a simple code capable of performing integration in Python on any function.
All right, thank you. Is there any questions? Does anyone have any questions?